We have 19. So welcome to the final day of our special session. This is the group of Freeman, Schlumprecht, and Zsák, and they're going to all be speaking under the same title, Banach spaces for which the space of operators has two to the continuum closed ideals.
Okay, thank you very much. Thank you very much for the invitation. I would have preferred to come to Lancaster, but I already, but okay, let's do it like this way. So as Kevin just said, this is we're making a series of 3 talks, Dan and Andras and me, and I have the easy part. I do the introduction and they have the technical part. Okay, so let me, now it doesn't work. Sorry. Why? Okay, so I think this we defined this already several times, but let's do it again. We have a Banach space X. The operators on this Banach space is denoted by L of X, and an ideal is a subspace of the space of operators, which is closed under multiplication from the left and from the right by any operator on X. And of course, a closed ideal is an ideal closed in respect to the usual operator norm. Now, for a subset of operators, J of T denotes the closed ideal generated by the elements of the subset. In other words, the smallest closed ideal containing T, and you can write it like this. It's really the closure of all finite sums of the form AG, TG, BG, BJ, where TJ is in your set T and AJ and BJ are arbitrary operators on X. I'm also interested in singly generated closed ideals, and these are operators generated by one single ideal. More generally, I'm actually also considering ideals of operators between 2 Banach spaces, which is more or less defined the same way. Subspaces is a subspace of the closed subspace of the operator from X to Y, closed under multiplication from the right by operators on Y and from the left by operators on, sorry, I said it wrongly. On the right by operators on X and closed by under multiplication of operators from the left by operators on Y. Of course, we had this already several times. The 0 ideal is an ideal and all the operators are an ideal, and this is what we call the trivial ideals. And of course, we only consider Banach spaces which have a basis and therefore enjoy the approximation property, which means the compact operators are always the unique minimal non-trivial ideal of operators in our case. Actually, I'm a little bit being much more restrictive, and I want to consider only spaces which have a one unconditional basis AJ. This is kind of, I mean, the theory about ideals in general Banach space is much richer, but in this case, we have a lot, the structure of the operators on X is very rich if you have a one unconditional basis. And we ask ourselves, what is the cardinality of closed ideals, or what is the cardinality of singly generated closed ideals on X? Now, some trivial or some easy estimation, of course, the cardinality of singly generated closed ideals, because you're dealing with functions on a countable set, more or less, it cannot be bigger than the continuum. And then the cardinality of closed ideal can, of course, cannot be bigger than all the subsets of the continuum, so it cannot be bigger than 2 to the C. So these are the trivial upper bounds for the number of singly generated closed ideals and the number of all closed ideals. Let me give a little short overview of the history. So this is the first result in this direction. Gochberg, Marcus, and Feldberg proved in 1960 that the compact operators are the only non-trivial ideals on LP or on C0. I kind of was wondering why it's of course not alphabetically ordered, but then I found out that Gochberg is the advisor, Marcus is the older student, and Feldberg is the younger student. So this is how the order came here, I think. So then, well, 44 years later, Niels, Charles Reed, and Roy proved that the C0 sum of L2n's has exactly two non-trivial ideals, namely the compacts and the operator, the closure of the operators factoring through C0. I think yesterday it was already mentioned by Max. And a little bit later, together with Niels and Anders, we showed the same for the L1 sum of L2n's. There's a little, because it's not a reflexive space. There's a little, I mean, it follows more or less the previous result, but there is a little bit, you have to handle a little bit because of the non-reflexivity. Now, among the spaces with unconditional basis, these are the only spaces for which we know exactly the set of all closed ideals. And there is kind of a very strange dichotomy, because for all spaces with unconditional basis, we either do not know the cardinality of the closed ideals and the cardinality of the single generated, or we know that these cardinalities are maximal possible. So in some sense, there are these three types of spaces for which we know exactly the ideals. And for all other Banach spaces, we either know that it's a huge number or we don't know the number. And it seems to be, after these recent results, starting with Bill and Gideon, it seems to be the generic case that we have the maximal possible number of ideals. Okay, so let me give you one of the spaces which was researched quite a bit after the Gochberg, Marcus, and Feldman result, is the case of LP plus little LP plus little LQ, where P, say, is strictly between 1 and infinity, and let's say P is smaller than Q. So Volkmann in 1976 proved that the operators on LP plus LQ have exactly two proper maximal ideals, namely, as you might guess, the one factoring through LP and the other factoring through LQ. Actually, earlier than that, Millman proved that the number of non-trivial ideals from LP. Okay, so sorry, I have to let's go back. So there are two maximal ideals, one factoring through LP and LQ, and all other ideals are closed ideals generated, sub-ideals from LP to LQ. And now Millman researched, proved that there are at least two ideals in this space of operators from LP and LQ by saying, and what he did is, okay, there's of course always the compact ideal, the ideals of compact operator, and then he proved that the finitely strictly singular operators are strictly bigger than the compact and strictly smaller than all operators. So well, later together with Tomczak, with Nicole, Vladimir Troitsky and Bunyamin Zari, we proved that there are at least 5 ideals. And a couple of later, I brought it up to 8. So, but in some sense, this was actually quite hard results. And then there was a big jump. Together with Androsch, we proved that LPLQ contains a chain of singly generated ideals of cardinality, the continuum. Okay, so this was, sorry, I have to go back. So this is the reflexive case. We are here strictly between 1 and infinity. Now, Sirotkin and Ben Wallace and Gleb, they looked at the non-reflexive case where L1 plus LP, LP plus C0, and L1 plus C0. So looked at these spaces, and they proved that the space of operators being listed above have at least omega 1 singly generated closed ideals. So they're using indices, index theory. They proved that they define a certain index and show that for each index there's an ideal, and so they cannot get to continuum because of the nature of indices. But they prove that all these the spaces of operators of all these spaces have at least omega 1 singly generated closed ideal. With a completely different method, Androsch and Dan and I, and he will talk, Dan will talk about this, we proved that actually this list above, with the exception of these 2 spaces, L1 plus C0, L1 plus L infinity, have continuum many closed, singly generated closed ideals. So I have here 2 closed, okay. So for this case, L1 and C0, or L1 of L infinity, Sirotkin and Wallace result is still the best possible. We know. Okay, now for Zilsen and Schreier spaces, well, it's well known, it's, for example, in the book of Kasatsa-Schurer, that Zilsen space has continuum many complemented spatial subspaces, spatial meaning generated by a basis of, by a subsequence of the basis, and therefore it must, of course, have continuum many singly generated ideals. Gaspers and Lung showed that for Schreier spaces of finite order, and this is that have also continuum many complemented spatial subspaces, and therefore, of course, continuum many closed ideals. And Kevin, Tomek, and Niels, they showed that Zilsen space and the Schreier spaces of finite order have continuum many maximal proper ideals. Okay, and then came Johnson-Schechtman, Bill, and Giddon, proved that the operators on capital LP of, say, 0,1 has 2 to the continuum closed ideals. So this was a little bang. So, and there's one argument in their proof which applies to many other spaces, and it's the following proposition. Assume, so this is kind of making out of continuum many singly generated closed ideals 2 to the continuum many closed ideals. So you assume that you have Banach spaces X and Y, and you have a family of operators indexed by the subsets of the natural numbers, which satisfy the following property for some constant C bigger than 0. So you have this family of operators, Tn, indexed by the subsets. So if M is almost a subset of N, meaning that the difference from M minus N is finite, then Tm should be an element of the ideal generated by Tn. This is the first. Secondly, if this is not the case, if M without N is infinite, then the distance of Tm to the ideal generated by Tn should be larger than this constant. Okay, so so we have this family with that important property. I mean, then you can argue the following way. For any subset, let me define for any subset of the subsets of natural numbers. Okay, there's something missing here. I put J of index A, the ideal generated by the Tn n in the set A. Then I take a subset of all the subsets of the natural numbers of cardinality, the continuum, consisting about pairwise almost disjoint sets. Of course, you can do this. And then you take the family of JB, B being a subset of this C, then this family are pairwise different closed ideals. So in particular, the cardinality of closed ideals must be at least, must be 2 to the C, 2 to the continuum. So once you have a family satisfying this property, you deduce that you have 2 to the continuum many ideals. Okay, let me prove this. It's not a hard proof. So let's say you have 2 subsets of C of this family of disjoint or pairwise almost disjoint subsets of the natural numbers. And let's assume that you have a set M which is in B but not in A. What you want to show is that the distance, so the distance of Tm to the ideal generated by the Tn n in A is bigger than C, and this means, of course, that J of A and J of B cannot be the same. So in other words, you separated any of them. So, but what does this condition mean? What does this condition mean? It means that for any choice of natural numbers, for any choice of n1, n2 to nk of the set A, and for any choice of k operators on Y, and any k choices of operators on X, the distance of Tm to this finite sum has to be bigger than C. So these operators are the ones which are dense in the ideal J of A. And then you have this thing. Okay, but now, if you take N to be the union of the N finitely many Ni, since M without the Ni's is infinite, also M without N is infinite. And thus, the distance of Tm to J, the ideal generated by Tn must be at least C, by our first condition in this star. Now, but now the Tni, they are of course in J of Tn, and thus this finite sum has to be in J of Tn, and our claim follows from the assumption that the distance from Tm and Tn has to be at least C. This was our, so, okay. So now using this proposition by Bill and Gideon, and combining them with already known result about singly generated closed ideals, we deduce that the following spaces with unconditional basis have generate at least 2 to the continuum many ideals. So from the Gasparis-Leung paper, it follows that Schreier spaces have this property, So this is now a list of spaces which have, let me go back here. So this is the important property. Let's see. Sorry. Here, this is the important property now, the existence of this family of operators, which implies that you have 2 to the continuum many ideals. And so now I'm listing spaces which have this property, which have this family of operators. Okay, let me go back. Okay, so for example, from what Gasparis and Leon proved, Schreier spaces of finite order have this property. From what Kevin, Niels, and Tomek proved, Schreier spaces of, and Zilsen has this property also. I mean, sorry, it follows from both. And now the result of Kevin, Niels, and Tomek can be generalized actually to all Banach spaces with unconditional basis, which are asymptotic little LP, but do not contain little LP. So this argument of these spatial operators can be generalized to all of them. Now, from what Dan, Anders, and I proved, we can also, this list of spaces, L1 plus LP, C0 plus LP, and L infinity have this family of operators. And now, and this will, Dan will speak about this. And also in the reflexive case, we have this family of operators, which have this property. Now, also Manusakis and Anna Pelcher proved that the space I constructed, the first arbitrary distortable space, has this property of, and Bill recently proved that actually even the LQ sum of finite dimensional LPNs for certain P's, namely P and Q on 2 different sides of 2, have this property. So let's say, okay, so let me give you, so in other words, the list of spaces for which we know is actually smaller. Oh, wow, what is it's infinite in both cases. But so let me make a list of interesting spaces for which we do not know yet what the cardinality of the ideals is. So the one is little L1 and C0 and little L1 of L infinity. This is actually an interesting case because we know already that there are uncountable many ideals, actually of singly generated ideals, but we really don't know more. Then the extreme case for the C0 sum of little L1 ends and the L1 sum of L infinity ends, we don't know. They actually are. I think Niels, Andros, Terodel, and I, we spent the whole summer in Cambridge not solving that case, right, Niels? So we worked very hard on that and couldn't get anywhere in these 2 spaces because it seems to be after the result of Niels with Charles, Reed, and Roy, this would be kind of the next step of an example of a Banach spaces for which the structure of ideals is quite simple. But now, so, and the other space, of course, the cases which do not satisfy is proposition, Bill's condition, and actually Schreier spaces of infinite order. We don't know yet. So I made that, I would say, if I had to bet, the first line of spaces hopefully kind of has finitely many ideals or a very bounded number of ideals. And the second line, I would guess, should be in the category of the spaces which have a lot of ideals, closed ideals. So, but this is only my guess. Okay, now so there are always there are always two parts to prove that you have 2 to the continuum many ideals. There's a general part. You want to have this family of operators, which has this condition star. There's a general part which kind of works for all arguments. And then there's a specific part, which is often quite technical, in which you have to show that specific spaces satisfy this general condition. So what I will concentrate in give you an idea of what you have to do always, or what you do in this, the common part of the proof. So, and then Androsh and Dan will speak specifically about LP plus LQ and or L1 plus LP and C0 plus LP. Okay, so how do you start constructing this family of operators indexed by the subsets of the natural numbers? So we have 2 Banach spaces, X and Y, which have a normalized unconditional basis EI, FI. Oh, I'm running out of time here. Okay. And so in some sense, everything is generated by only one operator. Namely, you have an operator from X to Y, which is kind of a block diagonal operator. In other words, you're blocking the bases EI and FI into FDDs, EK and FK, and then you have an operator which is like the amalgamation of operators of finite dimensional operators from EK to FK. Okay, and then so you have this one operator which is diagonal, and then for every subset you simply project down. You're looking at the projections because we have still an unconditional FDD. You're looking at these projections, and then you multiply the operator with these projections. So you have a family of operators. So then, of course, the first part of condition star is automatically satisfied. If M without N is finite, then of course Tm has to be in the ideal generated by Tn. So you seek conditions which secure that if M without N is of infinite cardinality, then you can separate the ideal Tn and Tm. And so let me quickly say how you separate it. Well, we know this from function analysis. We need functionals to separate. So you're giving yourself a finite set of finite sequence in the sphere of En, and a finite set in the sphere of the dual of Fn, which have the property that Tn applied to X and I, and then you apply Y star n is equal to 1. And then you're looking at a functional like that, where the P and I's are a convex combination, which in our cases are mostly simply the uniform 1 over Ln. And then you have automatically that this functional apply to the Tn is equal to 1. And now what you need now is, so how much time do I have? Not much, right? Kevin? No,
not too much.
Yeah, okay.
But I guess it's your session, so if you wanted to go over a little, then
I'm going a little bit over. Okay.
Yeah.
So it's what we need is we have these functionals, and we taking for every subsequence of these functions, we're taking a weak star accumulation points, and then have to satisfy this condition that everything in J of Tn, that this limit has to be 0. Okay, let me quickly go this. And now it kind of, so let me, so this, let me, okay. We have at the end, we coming down to the following condition, that some limit, and I hope that Andros and Dan will then explain a little bit more. So here we are only considering finite dimensional operators from EM to the first part of X, from 1 to M. This limit has to be 0. And here we are looking at any infinite dimensional operators from EM to the infinite part after M also has to go 0. These are the two conditions we have to satisfy. And now here there are 3 examples. In the case of the reflexive case, LP and LQ, the ENs will be finite versions of Rosenthal spaces or their duals, because once you go, and the FNs will be simply Hilbert L2Ns. And the TNs simply, the operators TNs will be formal identities. In the case LP to C0 is kind of there, we write the LPs as an LP sum of L2Ns, the C0 as a C0 sum of L infinity Ns in the trivial way, and then the Tns will be nothing else than restricted isomorphisms used in compressed sensing. In the Zilsen case, it's actually the E and the Fn are simply generated by the EJs are simply the TNs are simply the identity on subspaces, but the PNJs will not be uniform. There will not be 1 over Ln. Okay, sorry that I overran. And sorry for actually that I couldn't really explain the middle part. Okay, I'm done.
Okay. Are there any questions or comments?
Thomas, can you comment on the asymptotically LP not containing LP case? I mean,
okay, so
the same method as what you just said for C. Wilson?
Okay, so there are a couple of ingredients. First of all, there's the ingredient. Okay, let me go back. So first of all, it starts with what Kevin, Niels, and Tomek proved. Well, or the idea actually also Gaspris, Luang. Then what the second ingredient is, from what Ted, Odell, and I think Andros proved, you can find a subsequence in an asymptotic LP space, which is dominated by Zilsen of a certain order and has an upper estimate of the dual of that same Zilsen space. So this reduces the problem to only considering Zilsen spaces or their convexification of a certain order. This is the second step. And now the third step is you have to, and this is the new thing, you have to prove that modified Zilsen is equivalent to non-modified Zilsen. And this you need to prove that modified Schreier is the same as Schreier sets. This is the new ingredient. You have to show that. And this together with these 3 things, you can show it.
So what you are saying is that you are really using strongly asymptotically LP instead of just asymptotically LP. Also.
Actually, a side product of that. I mean, do you know what Gilles Pizier introduced also the term asymptotic LP. And and it's different from what Maury and Nicole, and it actually shows a side product of that is that in the unconditional case, they're actually the same. This is a side product, or up to passing to subs. Sorry, I should say a little bit. No, I'm a little bit vague here, but after passing to subspaces, it's the same, and having unconditional basis.
Thank you.
Yeah.
Niels, you had a question?
Yes. So on that page there, you mentioned the space little L1 direct sum little L infinity.
Yeah.
But I believe that in the prior paper of Bill Johnson and Johnson-Schechtman that they wrote with Gilles Pichier, in that one they actually proved that L infinity has continuum many ideals itself, right?
Oh, I missed that. Yes, it's. I think. Okay, so this is Bill. Is this? Yeah. Yeah. No, sorry. Yes. So this case is also solved. Yeah.
I'm not sure. I'm not sure we get 2 to the C many though.
Yeah.
But you certainly get you plug the gap between omega 1 and continuum.
Yeah.
Yeah.
Okay. Then.
Right.
Yeah. Okay. So Bill, this is a continuum, but you have in L1 plus L infinity continuum many ideals, or 2 to the continuum many?
No, in the paper with Gilles, we were getting only continuum.
Oh, okay, so then
that preceded, and we didn't look back. I don't.
Yeah. Okay, so then for little L1 and C0 plus C0, Ben Wallace and Sirotkin's result are still the best possible, and for that we know we have a continuum. Yeah. Sorry, I missed. Yeah, I overlooked that. Yeah. But we don't know whether it's 2 to the continuum many, right, Bill?
No, actually, we didn't. I think about it after Gidon and I did this other stuff, but
yeah.
But I don't think it works. I mean, mainly these are arguments on L1, and that we couldn't handle the L1 case, and L infinity comes via this duality argument from big L1, which is kind of a strange sign.
Yeah, right.
Ideals,
right. Okay.
Small ideals on bounded operators on capital L1 dualize to give you operators on L infinity, and they're different, which was kind of weird. And then capital L infinity is the same as little L infinity, of course. So that's the way the argument went.
Yeah, I think yeah.
Okay, are there any more questions? Comments?
Yeah, so the hidden thing here is that we don't know it for bounded operators on big L1. I mean, it's when you write it this way, you don't see that. But
right, yeah. I didn't list capital L1 because I wanted to concentrate only on spaces with unconditional basis. Yeah.
Right.
But of course, L1 has its special. It's yeah.
Well, little L infinity doesn't really fall into that category either, though.
I know. Okay, sorry. Yes, you're right. Yeah.
So
well, in some sense, it's almost the same as little 1C0 for this type of question. So yeah.
Where do these ideals sit with respect to, say, strictly singular operators? Or
they're very small.
They're all
small.
Yeah. They're all contained strictly singular.
While Bill and Gidon's, they are large operators, right?
Yeah, in bounded operators on capital LP, they're naturally constructed to be large operators, and then from that you can deduce that you also have small operators. Again, that's a little bit weird.
Yeah,
it's kind of a very formal and simple argument to go from getting the large ones to getting the small ones. We don't know how. If you have a bunch of small ones, we don't know how to go to large ones though. But from going from large to small, sometimes you can do with just some simple trick.
So this method, I kind of presented this kind of ideals which I essentially generated by one operator in some sense. They are all small, at least in the cases I know them. Well, not actually, not in Zilson case. No, sorry, I said wrong.
The Schreier and
But
Zierelson are large.
they're large, of course, right? Of course, they're yeah. But okay, in little LP plus LQ, they're even small. They're small. Then they're all finitely strictly singular. Yeah. Yeah, right. In Zilson, it's, so the main. So you either have a lot. Okay, so what are the reasons why we have these many? One of the reasons is if you have a lot of complemented subspaces. This is in LP plus LQ. Or like in Zilson spaces, you have this almost LP, but not LP. I think this is, yeah. Yeah. I think, I think I can stop share now.
Okay. All right, well, let's thank Thomas again for the talk. And who's next? Is it Andras or Dan?
I think it's me.
Okay. I could have looked that up, but I figured you knew. You have sharing capabilities and everything? Yeah. Okay.
Firstly, I would like to thank Niels, Kevin, and Tomek for the kind invitation. I'm just a bit sad that we couldn't all go to Lancaster. I'm also a bit sad for Garth that we couldn't give him a proper send-off, but I hope that will be rectified at some point. Okay, so this is the second in this three-part series of talks. And as Thomas said, I'm going to give an application of the general process that Thomas started talking about at the end, to show how to get to the continuum many closed ideals in the operators on LP plus LQ. So the aim is to that there exist 2 to the continuum many of these closed ideals. So first of all, as usual, we have operators on LP plus LQ, and we can think of them as 2 by 2 matrices with the following matrix entries. So you have the operators on LP, operators from LQ to LP, etc., operators from LP to LQ, and operators on LQ. Okay, so with the diagonal entries, we already know what's happening. So as Thomas mentioned, that there is only one non-trivial proper closed ideal on LP, and that's the compact operators, and of course the same for LQ. We also know that every operator from LQ to LP is compact because Q is bigger than P, and every operator in the other direction is strictly singular, which I will denote by S for the strictly singular operators. So, so one consequence is you immediately get the following ideals. You of course have the entire algebra of operators, and then you have the ideal of operators factoring through LP, when in this corner you only have compact operators, and vice versa. If you have compact operators only in the top left, you get the ideal of operators factoring through LQ, and these are the 2 maximal ideals that Thomas mentioned. And in every other ideal, the operators in these 3 entries are all compact. So really what determines the ideals is this corner, the bottom left corner. So basically we are now reduced to considering operators from LP to LQ, which is again the strictly singular operators from LP to LQ, same thing. So at this point, let me just recall the definitions here. So if an operator T between Banach spaces X and Y, then this is strictly singular if it's not an isomorphism on any infinite dimensional subspace. And another way of saying that is as follows. So if for every epsilon and for every infinite dimensional subspace of X, you can find a vector in Z so that the image is small compared to X. So if X is norm 1, then the image has norm less than epsilon. I immediately also define what it means to say that T is finitely strictly singular, which was also mentioned in Thomas's talk. So the difference is that given this epsilon, you don't need infinite dimensions to find a vector that maps to a small vector. You can find them in large enough finite dimensional spaces, and how large, it depends on epsilon. So there exists some n, a natural number, so that for every subspace E of x of dimension at least n, there exists a vector x with norm tx less than epsilon norm x. So it quantifies what it means to be strictly singular. So it's obviously formally a stronger property. Thomas mentioned the history of searching for ideals in this space of operators from LP to LQ, and the first step was Millman's observation, which goes as follows. So you have of course, the trivial ideal, then you have the compact operators, which is the unique smallest closed ideal, and then on the other side, you have the entire space of operators, which are strictly singular. And then what Millman observed is that there is another ideal, and this is the ideal of finitely strictly single operators. And that's a new one, so it's different from the others. I should have said that it is not too hard to check that these are indeed closed operator ideals. I suppose the finitely strictly singulars is not quite so trivial. You can do it by bare hand, or there is an elegant argument using ultrapowers. I'm going to explain how you prove these two strict inclusions, because it brings in two ideas that will be used later. So for this strict inclusion, an example of something that is finitely strictly singular but not compact is the inclusion operator. So consider the inclusion, which I just denote by I, from LP to LQ. Okay, so LP is of course a subset of LQ, so we just map X to X. If you consider, just for example, if you take the vector X with coordinates n to the -1 over p n times, and then followed by zeros, so that n here. So I call this a flat vector. So in the LP norm, this is of course has norm 1, but this mass of 1 is sort of distributed over a long support. So the L infinity norm is very small; it goes to 0. And for such a vector, of course, the Q norm, because Q is bigger than P, is going to be very small. So the motto is that this inclusion map maps flat to small. So flat vectors go to vectors of small norm. So that's one important observation. And then what Millman proved, it's a very nice little lemma about inner algebra, that if you have a subspace of C0 of dimension n, then you can always find a vector x in E such that the sup norm is obtained at least n times. So this is modulus of xi for at least n values of I. Okay, so obviously, if let's say this has norm LP norm 1, then of course this sup norm is small. So we have a flat vector, and because the inclusion maps flat to small, what this shows is that if n is large enough, then in any n-dimensional subspace of LP, you can find a vector that maps to a small vector under the inclusion map. So in other words, we prove that I is the inclusion map finitely strictly singular, and obviously not compact. So this idea of flat vectors will come in later on. Okay, so that's the first inclusion being strict. How about the second one? So we need to find an operator from LP to LQ that is not finitely strictly singular. So for that, Milman used the following observation. So what Kinchin tells us that the Rademachers span a copy of L2 in any of the LP spaces, and in the reflexive range, these are complemented. So in particular, if you take the first n Rademachers, which gives you a copy of L2n in capital LP, they are complemented in capital LP. So embeds complementarily into LP. And in fact, because those Rademachers generate a sigma algebra with 2 to the n atoms, it lives in LP 2 to the n. And this complementation is uniform over n. And also the isomorphism is uniform. And that means that if I take the direct sum of L2n's in the LP sense, then this is going to be complemented in LP, and by Perchinsky LP is prime, so this is going to be isomorphic to LP. So this is using Perchinsky. And of course, you can do the same on the other side. So you have the LQ sum of L2n's, and this is LQ. And then you take as an operator, and these are the type of operators that already Thomas talked about. So, and again, that comes in later as well. So we'll be looking at unconditional sums of finite dimensional spaces, and we look at diagonal operators. So in this case, you take a very simple diagonal operator, namely you map L2n to L2n via the identity map. So this is the identity on L2n. Okay, so so obviously, because we're going from P to Q and Q is bigger, this is a bounded operator, and this is not finitely strictly singular, because there are finite dimensional subspaces of arbitrary large dimension in which you cannot find the vector that maps to a small vector, because you have an isometric map at each level. Okay, so that's how you find one ideal. So now let me go to jump straight to showing that there are to the continuum many ideals. So for that, I'm going to fix P to be strictly between 1 and 2, whereas Q can be arbitrary, strictly bigger than P, of course, and finite. And the general case will then follow by an easy duality argument. Okay, so I'm going to also let P prime be the conjugate index of P. And again, as Thomas already said in his discussion about that general case, we basically will have one operator. It will be a diagonal operator. So again, we're going to write LP in the form of an LP direct sum of finite dimensional spaces. Whereas on the other side, with LQ, we do the same as before. It will be the LQ sum of L2n's. So that won't change. So what are these finite dimensional spaces we are using in LP? And this is where the Rosenthal XPW spaces come in. So for M in N, we're going to fix a weight. It's not too important what it is, because I won't have time to go into any of the sort of calculations and technical discussions, but I'll just tell you anyway. So it's m to the minus eta, where eta should be something obviously positive, but strictly less than 1 over P minus 1 over 2. So you want it to tend to 0, but with some control, not too fast. Okay, and we're going to consider the following space. It's going to be Rm with this P prime Wm norm. So the parameters are the exponent, which is P prime, the conjugate of P, so that's strictly bigger than 2, and we have this weight. So what is this space? So it's a sort of mix P prime and L2 norm. So the norm of a sequence AI in this P prime Wm sense is the maximum of the LP prime norm and a weighted L2 norm. So it's WM times the sum AI squared to the half. Oops, right. So obviously, the L2 norm is bigger than the P prime norm, but we have this small weight in front. So the idea is that if you have a kind of PQ vector, let's say a basis vector, that has norm 1 in both the L2 and the LP prime norm, but of course, because of the weight, it's the P prime norm that wins for a PQ vector. Whereas if you have a flat vector, then say the AI is 1 for all I, then of course, because of the choice of the weight, it's the other side that's going to win. So they are kind of playing against each other. Okay, so now what I want is a subspace of LP. So I want to go back to LP. So we're going to look at the dual space, the dual of this. So that's going to be my EM. Oops. Okay, the dual of this space. And of course, in this space RM, in the pre-dual, you have the standard basis vectors. So in EM, we have a basis, namely the bi-orthogonal functionals. So EM has an unconditional basis, which I will denote by XMI. I is between 1 and m. So it's normalized, it's 1 unconditional. And what we need to know about this is that if you add up some of these vectors, so if you take the sum of the base vectors over I in some subset A, then the norm of this is approximately the following, and that's just an easy computation. So in the pre-dual, we have the exact formula for the norm. So in the dual, you can do a maximization, and it's easy to see that it's going to be of the following form. Up to some constant factor is going to be k to the this is going to be exactly k to the 1. Oops, this is going wrong. Oops, sorry, this is misbehaving. So it's 1 over p and the minimum of 1 over the weight, k to the half, where k is the size of the set A. So as I said, it's an easy computation. And one thing that we observe immediately that, of course, we are far from little L1, which I think Thomas mentioned. But if not, I'm going to explain why this is relevant in a moment. Okay, so what Rosenthal, one of the things Rosenthal proved is that you can actually realize these this basis up to some constant that depends only on P and not on the weight or on M, the dimension, as a sequence of independent random variables, each of which is symmetric and 3 values. So it's kind of the next step from the Rademacher functions, which are 2 values. And here you have values 0, some plus C and minus C. So they live inside capital LP, and it's complemented in LP. And again, the complementation constant depends only on P. So it doesn't depend on the weight or the M, the dimension here. So again, what we have is that this EM is sitting inside capital LP. And because, again, these are 3-valued random variables, the sigma algebra they generate will have 3 to the m atoms, so it sits inside LP of 3 to the m, complementarily. And this comes from Rosenthal's work on this. Okay, so again, what we can do, we can view LP as the LP direct sum of the EMs. So again, this is because this is naturally a complemented subspace of LP. So by Pelchinski, it's isomorphic to LP. And as I said before, on the other side, we don't change anything. We can continue looking at LQ as the LQ sum of L2s. And then the operator, we have a single operator T, which will eventually generate everything. And this is the diagonal operator. So maybe I should put an M here to match the M on this side. So this is the diagonal of operators Tm. And Tm is going to be, of course, an operator from Em to L2m, which maps, it's basically the formal identity map. So with respect to these bases. So it maps some AI xmi to some AI, let me call it E sub mi. So this is nothing else but the standard basis vectors, the standard orthonormal basis of L2m. Okay, so and then you get this continuum many ideals generated by single operators, and the single operators are these operators you get from T by projecting onto infinite subsets. So if you have M is a subset of natural numbers, infinite, then Tm, T capital M, this is T composed with a projection onto M. So projection M, let me just write this down, of a sequence Xn is the sequence Yn, where Yn is Xn if n is in M, and 0 if n is not in M. Oops. Okay. Right. So what we need to do is, as Thomas explained, in general, we need a separation Tm from the ideal generated by Tn when m minus n is infinite. Okay. So and then, as Thomas explained, from the paper of Bill and Gideon, that once you have that, you can soup this up to get 2 to the continuum many closed ideals by this general procedure. Now, in order to do the separation, Thomas introduced this in the previous talk, these functionals, which are sort of trace-like functionals, and the trace of Tm should be 1, whereas that trace should disappear on the ideal, and then you get the separation. And in order to get the trace disappearing on this on JTN, on the ideal, you need the following fact. So what we then need is that if you take the average 1 over m sum I equals 1 to m, and you take the basis vectors xmi, and you apply an arbitrary operator b, which is an operator on LP, and then you map it over by Tn to the LQ side. So the average of the norms here should tend to 0 as sorry about this. I'm not sure why this is misbehaving. So this should tend to 0 as m tends to infinity, with m in big M, not in little m, not in big M, sorry. So once you have that, then you can prove that these functionals that Thomas introduced will vanish on the ideal generated by Tn, and then we are done. And then to do that, again, Thomas already hinted at how you do this. You have to split this operator B into two parts. So this should be true for any B. On LP. Of course, I still think of LP as this LP direct sum of these spaces EM. So this quantity is at most, by prime quality, the following 2 sums. So it's similar splitting as appeared on Thomas's slide. So let's call it B1 and B2. And I'll just write down in a moment what they are. So B1 is B followed by the projection onto n in n, where n is strictly less than m. So this is the earlier part, the finite part. So this will be the one that is easy to deal with. and B2 is the later part. So projecting onto n in n with n bigger than n. And because m doesn't belong to n, obviously B1 plus B2 is B. Now, I sort of cheated here a bit. I said I'm taking the Dirac sum of all the EMs where m is any natural number. Actually, what we really do is instead of taking all natural numbers, we take a very lacunary sequence of natural numbers to make sure that, for example, m is a lot larger than any of the previous m's. But I didn't want to make the notation worse. So let's just pretend that the natural numbers increase rapidly. So the first part is easy to do with, because what you're doing is you have m vectors, and m is much, much larger than the rank of this finite rank operator. So you're squeezing a huge amount of vectors into a small dimensional space. So by pigeonhole principle, simply many of these vectors are aligned, almost aligned. So the images add up like little l1, but the XMIs don't add up like little l1. So you would get a contradiction with boundedness of these operators unless this average is actually small. So that part is fine, is easy. Is the second part that is interesting, and that part consists of two parts. So the first thing you have to do is to show that this operator Tn maps flat vectors to small vectors. And that's sort of believable because we go into an LQ sum of L2n's from an LP sum, and P is less than Q, of these EMs. And the XMIs are on unconditional basis, so there is certainly a lower L2 estimate, which actually I should have said earlier. I should have mentioned is that the reason, of course, these operators Tn are uniformly bounded is because XMI being an unconditional basis in LP, there is a lower L2 estimate, and the constant depends on the cotype 2 constant. But because we have this more precise formula for the sum of XMIs, it's a computation to show that this fact that this operator T maps flat vectors to small vectors. So that's not too bad. It's not too pleasant a computation, but that's fine. It can be done. Perhaps the more interesting bit is the next bit. What you want to show, therefore, is that this B2. So this is the part that maps the XMIs to the later parts. The much bigger. Remember these, as I said, these n's are really very lacunary. So the n's appearing here are much bigger than the fixed m. So what you're doing, you are mapping these XMIs to the right. So what you need is that is the following, that basically the B2 XMIs are mostly flat vectors. And because flat vectors map to small vectors, and most of them are flat, the average will be small. So what we look at is the set of coordinates nj. So this is n is bigger than m. I could also insist that n is in big M, but that's not important. J is, of course, between 1 and n. And the nj coordinate of B2 of XMI is large. It's at least some delta for some I. And what you need to show is that the size of this set is little of m. So if you divide by m, it tends to 0. What is this delta? It comes from this property that Tn maps flat to small vectors. So if you want the small to be epsilon, then there is a delta that if your vector is delta flat, meaning the subnorm is less than delta, then it maps to a vector of norm less than epsilon. So this is that delta. And so you look at the bad situation when you have large coefficients, and you want to say that this doesn't happen too often. And just roughly to explain what's happening is the following. So you have the XMIs. In the domain, you have these M coordinates. So these are just the numbers from 1 up to M. And when you look at the image, the coefficients, they are supported on this set of all NJs, n bigger than M, J between 1 and N. And so let's say you look at, I fix one of them. I fix a particular coordinate NJ, and I look at all the values of I that satisfy this condition, so that the image of these basis vectors have large coefficient on this coordinate. So again, that would mean that the image vectors add up like L1, but that can't happen for the XMIs. So that just means that the number of the I's here cannot be too large. So the size of the bad I's is sort of proportional to the size of this set, of the set of bad NJs. So let's just pretend that roughly it's equal. So the number of bad I's here that map to something which is not flat, and the number of NJs is the same. Let's just pretend that. So then what you want to show is that if you have a, let's say that size is, I don't know, K. So you have a sum of K vectors here, and the image has K large coefficients. So why can this happen? What you need to show is that, well, you already know the upper bound. How big can the sum of K vectors be? We have this formula for that sum. Here it is. So the sum of K vectors is at most that. And that K is at most M. And if you have a, so if K is large, remember we want this to be little o of M. If it's not little o of M, so it's proportional to M, then basically this is going to win. Whereas if you look at the image, you have LQ sum of L2Ns, and you want to then, sorry, it's not the image, I'm sorry. Now you're looking at the, this is still the B2 maps LP to LP. So what you have to consider, what happens if you add, let me go back to the formula here. So now you're not adding XMIs, you're adding XNJs. And how many is sort of something proportional to M. So this K is proportional to M. But what you're dividing by here, the WN, is going to be very small. So sorry, I said it wrong before. So in the domain, this will win, the 1 over P. In the range, this is going to win, and it's going to be much bigger. So you're trying to map a vector of certain size to a much bigger vector, and that contradicts the boundiness of the operator. So we have that will then prove that this set has to be of size little o m. So most of the XMIs must map to flat vectors. So on average, Tn will map them to small vectors, and that sort of completes the proof. Let me just finish by mentioning a few other things. So, of course, one thing I think perhaps Thomas mentioned this already, that if you have P between 1 and infinity and P is not 2, then LP plus L2 is complemented in capital LP. So we deduce from this that in capital LP there are 2 to continue many closed ideals. So that was done earlier by Bill and Gideon, and they found these large, as discussed before, these large ideals, whereas ideals we have here, as Thomas mentioned, they all live inside the ideal of finitely strictly singular operators. And the other thing I also want to mention is that if you look at the proof carefully, then we don't necessarily need to work with LP and LQ. You can write down some general conditions and a class of spaces that this argument applies to. So you can show that if X is one of, well, of course, LP is one of them, but it could be P convexified Syllarson space or the dual of P prime convexified Syllarson space. And then similarly, Y is one of the corresponding space on the other side. Then the operators on X plus Y will have to do the continuum many closed ideals. Oops. Okay, so I remember that Dan mentioned the story of when he gave a talk in Banff. He was similarly giving it was I think a double talk, and he was second, but the first speaker went way over time, and he had to improvise. So I think I stopped here to make sure that he has plenty of time. Thank you.
Okay, thank you. Yes, this is an interesting format with the three speakers, but I think it's working well. Are there any comments or questions? I'm sure Dan has lots of comments and questions.
I think Niels hands up.
Thank you for a very nice Blackboard lecture, Andras. I could almost imagine you standing in front of the large blackboards at the math department in Cambridge. So one thing that has always puzzled me a bit about this proof is that the functional you use to separate your operators, right? You could choose that from all of the dual space of B of X, which is a vast space, but you actually take it from the pre-dual, which is a very, very small space. Have you any thoughts about that?
Well, then we take weak star limits.
Yeah.
Right? I mean, the real functionals will be weak star accumulation points of that functionals, right? So it's
you're basically using the density. I mean, the fact that the whatever it is, the space is weeks whatever dense in its in all of its second dual, right?
The real so the functional which ends up separating Tm from the ideal generated by Tn is the weak star limit of this functional over M.
Yeah, so you have these finite traces, and then you take the weak star accumulation point of those.
Sure. Okay, that makes sense. Thank you.
Are there any more questions? Comments? Okay, thanks again, Andras and Dan.
Okay, so
well, our final speaker is Dan Freeman to close this out here at IWOTA, special session 16. So take it away, Dan.
Okay, so thanks a lot. So this is the third part of a talk. And so if you're just logging in now, quickly go watch the other ones on YouTube. And thanks a lot to Niels, Tomac, and Kevin for the opportunity to speak. I think this has been a really great session so far, so I'm really happy to be a part of it. Okay, so I'm quickly going to go through some notation that we've all seen a bunch of times so far now. So we're using L of X to be the space of bounded operators on X. And if we have two Banach spaces X and Y, this is a space of bounded operators from X to Y. And if we look at a subset of L of X, we're calling that an ideal if whenever you multiply by the left or the right by an operator, you stay inside that subspace. And so this coincides with the usual algebraic notion of an ideal. We're also going to look at subspaces of L of XY, where now you operate on the left by something in L of Y and something on the right by something in L of X. And we're particularly going to look at if you consider a single operator. We'll use this notation to denote the smallest ideal generated by that operator. And then if you have a collection of operators, this is the notation for the smallest ideal containing that whole collection. And Andras gave a great explanation of this. And so if we have a specifically look at the case X is LP and Y is C0, or X is LP and Y is LQ, where Q is bigger than P, then this should be L of X plus Y. So then the maximal proper ideals of the direct sum, L of X plus Y, are the closure of the operators which factors through X and the closure of the operators which factor through Y. And then what we have is all non-maximal proper closed ideals of this space can be naturally identified with all closed ideals of the operators from X to Y. And so the idea is, if we're interested in knowing how many operators there are in the space of bounded operators on this direct sum, really what we need to do is study this here. Okay, and so Androsh showed that in this case, the bounded operators from LP to LQ have exactly 2 to the continuum enclosed ideals. And what I'm going to talk about is the non-reflexive cases. And so I'm going to try to give a argument to prove that the space of bounded operators from LP to C0 has exactly 2 to the continuum closed ideals. And then by duality, if you look at the space of bounded operators from L1 to LP, that will have 2 to the continuum, and then dualizing again, we have the space of bounded operators from LP to L infinity has 2 to the continuum closed ideals. Okay. So the first thing I want to do is to just recall the setup that Androsh talked about. We have inside little LP, we have these uniformly complemented subspaces En, which are finite dimensional. And so I have some finite dimensional subspace of LP, E1, and I'm going to look at L2 of that dimension. And because they have the same dimension and E1 has a given basis which uniformly dominates the basis, sorry, this should be here. And so E1 has a basis which dominates the basis for L2. And so I can look at a matrix, which is just the identity. And so T1 maps from E1 to L2 of that dimension. And then E2, I'm drawing it bigger because its dimension is much bigger, is a bigger finite dimensional subspace in LP. And then we look at L2 of that same dimension. And then we have this identity matrix that goes between them. And then we keep going. Oops. Okay. And so on the left here, these are all uniformly complemented finite dimensional subspaces of LP. And so if I do the direct sum with the P norm, Pelczynski says that this is isomorphic to little LP. And because Hilbert spaces, finite dimensional Hilbert spaces, are uniformly complemented in LQ, if I do the direct sum over here with the Q norm, this is isomorphic to little LQ. And so what we have in Androsh's setup was finite dimensional spaces in LP, and then operators which map this finite dimensional subspace to the Hilbert space of the same dimension. And the operators are really simple. It's just maps the basis to the basis. The reason why this is able to generate lots of different operators that generate different ideals is the geometry of these subspaces are all very distinct. And that is what we're able to use. So the reason why this setup won't work in the non-reflexive case is that if I change this P to L1, what's going to happen over here is that if I'm picking complemented subspaces of L1, which are finite dimensional, we're not going to have the same rich structure of different finite dimensional complemented subspaces. And so this won't work. We can't build these EJs if we replace this P with 1. And also over here, we use that LQ is isomorphic to the Q sum of L2Ns. But if I changed, instead of looking at LQ, if I change that Q to infinity, we have a problem because L2Ns aren't uniformly complemented in C0 or L infinity. And so this setup won't work for the non-reflexive case. And so let's think about what we would have to change. So in the LP-LQ case, we have the geometry of these spaces is really special and interesting, but the operators are the most boring operators that you could imagine. They're just the identity matrix. And so what we're going to change is these spaces here are going to become boring, but we're going to pick very interesting operators. And so that's kind of the theme for what we'll do. Okay, so here's the setup for looking at bounded operators from LP to C0. And so on the left, I'm going to look at subspaces of LP. And now P can be anything between 1 and infinity. And so the argument that we use for any P should also work for L2. And so what do I pick for my subspaces of LP? Well, if it's going to work for L2, then I'm going to have to pick L2 of some dimension on the left. And then now I need to pick finite dimensional subspaces of C0, which are complemented. Well, the only one I know of is finite dimensional L infinities. So what's changed from the previous setup now is here on the left, we're only going to look at Hilbert spaces. On the right, we're going to look at L infinities. But now we're going to look at an interesting matrix that goes from our Hilbert space to L infinity. And so this T1 is no longer going to be square. It's going to be very, very tall and thin. And so the idea is that K1 is going to be much smaller in dimension than L1. And so this matrix is going to look like, we can think about the rows as, say, X11, and then this will be X1, K1. And And so then we'll look at the next case. Oh my gosh, I just realized that I'm using too many L's. So L is the dimension on the right. So then here's T2. And so this is another tall, thin matrix. It's supposed to be X2, 1, be X2, L2.
I think we cannot see.
Not seeing what you're writing. It's not showing up somehow.
Oh
Doesn't
no.
show up.
Okay.
The first one showed, but then
Okay, so this is what happened last time. Okay, so let's see if this will work. Okay.
oh yeah, now it shows.
See it now, yeah.
Yeah, so unfortunately, you see all the behind the scenes stuff too. So it's less cool. Okay. Okay, so we have on our spaces are just our boring old Hilbert spaces on the left and L infinities on the right. And then our matrices are tall and thin, and they're getting much taller and much thinner very rapidly. And so then on the left, if we look at the P sum of these spaces,
No,
Pelchinsky.
you mean, yeah.
So we have L2s, finite dimensional L2s. If we look at their P sum, that's isomorphic to little LP. And then if we look at the infinity sum, this is isomorphic to C0. And so what we have now is we're going to construct operators where if I restrict to this piece, I send a small dimensional Hilbert space to a huge dimensional L infinity. Okay. So let's think about in the general setup of what Thomas talked about. So we have LP, we have C0, and then we represent them as a direct sum of finite dimensional pieces. We have some cool operator that goes between the corresponding finite dimensional pieces. And then for every infinite sequence of natural numbers, we have an operator that goes from LP to C0, which is block diagonal. And on each block, it is TM if M is in that sequence, and it's 0 if M is not in that sequence. And so the idea is that we're going to make an operator by picking a subsequence and choosing the finite dimensional ones that are in that subsequence to form our full operator. Okay. And so the goal is that if you pick two different sequences of natural numbers, if you have a sequence and we remove n from it, if this is infinite, then the operator for that sequence is not contained in the ideal generated by the other. We actually need the stronger case that the distance between the operator and the ideal is bigger than some uniform constant. And then the Johnson-Schechtman trick says that if you take a pairwise almost disjoint sequence of natural numbers with cardinality of the continuum, and then if you look at all of the different ideals generated by operators in that subsequence. This will be a set of distinct closed ideals with cardinality 2 to the continuum. And so Thomas talked about developing a general principle for this setup where you have operators in this form. And the key things that we have to prove now that we're in this really nice setup is these two conditions. And so Andras talked about these as well. So the first says that, so in this one, essentially it's saying that the operator Tm, so if I just look at Tm, so this does not factor well through the operator T from 1 to n. And so I have this finite dimensional operator, and I can't factor it through the ones that come before it. This is really easy to do because I can pick the dimension of this to be much, much bigger than the dimensions of the ones that come before it. So there's no way you can factor this operator through very small dimensional subspaces. The next condition is much more difficult. And so it says that Tm does not factor well through the ones that come after it. Okay. And so this one, this first condition, this is easy. Let's just forget about it. And then let's focus on this one here. And we have in the very specific setup that we have that we're mapping into, this is an L infinity norm. And so our range is L infinity or C0. And so this norm is given by a supremum. And so we have, what we have to do is prove that the average of these supremums goes to 0. And so because we're in this nice specific general setup, if we prove this, then we have proven that we have 2 to the continuum different ideals, closed ideals. So let's think about how to do that. And so this is the aside for applied math. And so the idea of compressed sensing is we have a huge dimensional space, and we have some signal in this huge dimensional space that we want to measure. And we only want to do a small number of measurements, though, to identify it. And so the idea is, let's say somebody's in an MRI machine. There's a huge number of possible different MRI images. And so the collection of all possible MRI images is very high dimensional, but you only want them to spend a small amount of time in the machine. So you want to do as few measurements as possible to identify what the doctor wants to know. Okay, so I think that's probably the most famous example for compressed sensing is motivated by these MRI machines. I don't know what the second most famous is, so I'm going to say it's possibly constructing ideals on Banach spaces. Probably not. So let's think about what's going on here. So we have a vector in this huge dimensional space is called K sparse if it has at most k non-zero coordinates. And so we think about X is, it's looking something like lots of zeros. Let's say it's A J1, then lots of zeros, AJ2, then say AJK. And so this is our vector X. It has tons of zeros and only k non-zero entries. And then we say that a matrix has the restricted isometry property if, when I restrict the matrix to vectors of this form, their norm is almost preserved. And so the idea of this restricted isometry property is that if I'm only interested in signals that look like this vector, then using matrix with the restricted isometry property works almost as well as using the identity matrix. And so this was made famous by Candes and Tao, who proved that you can find RIP matrices where the number of rows is, so if I do the number of columns, log of the number of columns divided by the number of rows is bounded by some constant. And so what's going to happen here is we're going to have an RIP matrix that, if I look at the columns, so this is n by n, this is going to be a very short, fat matrix. And so if I apply it to this vector, I get some let's say, let's call it JJ. And so I've applied it to this sparse vector, and the restricted isometry property then says that this norm, the norm of this is less than or equal to 1 plus delta. And we're going to normalize it. Let's see. So this would be the L2 norm of the AJs. Okay. So what this is saying is that if you have an RIP matrix, the columns, if you look at any k columns, it looks really close to being like an orthonormal basis. And the really cool thing about it is that you can have the number of columns be exponentially big according to the number of rows. And the way that you prove this is pick a matrix at random using either, you could pick these randomly Gaussian or randomly plus or minus 1 in each entry divided by square root of n. If you look at specifically the case for RIP for k equals 2, that's exactly the famous Johnson-Lindenstrauss lemma. But the main thing for us is that you can find these matrices that look like the identity, or look like an orthonormal basis for small numbers of columns. Okay. So back to ideals. we're going to pick Km and Lm. And so recall Km is the dimension of our L2 and Lm is the dimension of our L infinity. And we can pick Lm. It's possible, according to Candace and Tao, to pick Lm exponentially bigger than Km, but we only need it just bigger by this factor of m to the fifth. And so Candace and Tao, they're greedy. They say this can be exponentially big. We only need it just a little bit bigger. Okay. And so we have it so that it has the RIP property for the previous dimension L infinity. And so if you take any set of less than Lm minus 1 vectors, it looks too equivalent to an orthonormal basis. And so Candace and Tao says that we can do this. Okay. And then now, let's recall what we have to prove. So in order to get two to the continuum different closed ideals, we need to prove that this goes to 0 as m goes to infinity. If we pick Km and Lm with this setup, we actually we only need, we have that this is this bound here. And the way that we would prove this is that first, here we have a supremum over these xni's. And we prove that there's actually very few xni's where this supremum is big. And once we prove that this supremum is big for only very few xni's, then we prove for each xni, there are very few xmj's where this supremum is big. And so the idea is that this value here is going to be very small for most j. So maybe I'll pretty much out of time. And so the first thing that we would do is prove that there are few xni's where this is big for some xmj. The way that we would prove that is you look at a collection of pairs ni where b star of xni is greater than or equal to 1 over m. And we also want to add this condition here because we know we have the restricted isometry property for vectors of that size. And then you just do a straightforward calculation, and to obtain that the number of vectors has this bound here. And so the number of vectors where xni, where this could possibly be big, is bounded by m squared km. Then we do similar calculations to prove that for each xni, there's very few vectors xmj where this is big. So if we fix some xni, if you look at the j's where this is bigger than or equal to 1 over m, then we would find that the number of those vectors is bounded by 2m squared. So I'm going kind of fast because I'm out of time. And so what we have is that the number of vectors where this is bigger than 1 over m is at most this. We just multiply those two estimates together. And then all the other vectors are at most 1 over m. And so what we have is that this value here is bounded by 2 over m. And all we need to show is that this goes to 0. And so this would complete the proof. So thank you very much.
Thanks, Dan. Very nice talk. Thank you, Dan. To conclude the session, any questions or comments?
Very humble to call it only the second most important application.
I said maybe. It's maybe the second most famous application.
Well, I don't.
I laughed when you said that, but I felt like, you know, nobody was showing their screen. So, but yes, I appreciated what you said.
Okay, thank
I just
you.
couldn't show my appreciation. I actually did a thumbs up because I appreciated it. But yeah.
I previously had a different joke, and that part, and I told it to my wife, and she disapproved, and so I was like, okay, I'll find a better one. She said that this joke wasn't very good, but at least it wasn't as bad.
No, I liked it.
Will you go back to the definition of the operator using RIP?
Oops.
Thomas, didn't you say this was?
Oh, okay. So I should mention something. So this is specifically for the case P = 2. So I simplified things a lot here.
Yeah, previous page.
This.
So what is the matrix that you use? Any RIP matrix?
Well, it's the adjoint of it.
Yeah, we use the adjoint because the idea is that RIP matrices go from a huge dimensional space to a small one, and we want to go from a small dimensional space to a huge one.
Okay, right. So you take any RIP matrix going from n-dimensional L2 to little n, but you want the adjoint, you want it going back the other way, and then you just considered it as mapping into L infinity of that dimension. Is that right? Because
right.
That's the next. Oh, okay, right. Okay, right. That's what it works. And this is Candace-Tau. Well, of course, you went outside of Banach space theory. Of course, the Candace-Tau theorem is a one-line corollary of JL.
This is true. I'm sorry. I should have been more.
But it's a brilliant definition, the RIP, you know, and kind of encapsulated everything. But there's, of course, there's nothing to the proof, but the definition is really important.
Yeah, you're absolutely right. Of course, I should have been more clear on that. Yes. So essentially, RIP says that these vectors act like an orthonormal basis, and then the Johnson-Lindenstrauss lemma says that any pairs of the xj's are really close to being orthogonal, and so the collection would be close to an orthonormal basis. And so
Okay. Any other questions or? All right, well, let's conclude the session. Thank Dan and everything. Yay. Oh my gosh.
So can I ask a quick question relating to your list, Thomas?
Yeah.
So it seems to me, so the outstanding separable space you had was little L1 plus C0, right?
Yeah, this is the kind of the main, yeah.
But if you replaced one of them by one of the very nice spaces where we know there are 4 closed ideals, so either the C0 sum of L2n's or the L1 sum of L2n's.
Yes,
and then
this
of course
works too. Okay.
Then
So
it's true, right?
Yeah, Dan's argument actually works for the L1 sum of L2n's. Actually, it works whenever you have, whenever you have L2n's nicely complemented in it. The left side. The right side, so the right side has to be always C0, right? Then we couldn't do anything.
So whenever you have the left side has L2 ends uniformly complemented, and
Yes.
the right side has L infinity ends uniformly complemented. And you also have to have the direct sum of these finite dimensional subspaces on the left has to dominate the direct sum on the right.
Yes, yeah.
But does that mean that if you look at the C0 sum of the L2 ends, direct sum little l1, do we not know how many ideals? I mean, that there are 2 to the C in that one?
So if you have the L1 sum of L2 ends and the and C0, yeah. Oh, I see. And then you look at the dual of that, but then, yeah, that should work, I think.
You think you can do that one as well? Because I think we agreed we could do the dual by what you said, but not necessarily that one, right? Now we have the L2 ends uniform on the left-hand side.
Yeah.
Right? No, sorry, on the right-hand side, or
on the left side, you have to do the L2 ends, yeah, complemented.
yes, you need it on the left-hand side. So that means you have to have the L1 sum of them because you're going from the L1 sum to C0, not the other way around. Otherwise, everything goes crazy, right?
Yeah, right, yeah.
But then you can't dualize, or then you can. No, then you can't dualize, because if you dualize the L1 sum of the L2 ends, then you get the L infinity sum of them. So then you're out of the
Yeah, you're out of the thing, yeah. Yeah, it's kind of a question how many complemented subspaces you have. This is really how many different complemented, well-complemented finite dimensional subspaces you have. And let's say in Zilsen and Schreier, they are all spatial, right? You have the spatial spaces, and in LP and LQ, you have a lot of, you have the Rosenthal spaces and things like that, yeah.
Bill, I have a question. Do they cite your the JL paper in Candice Tao?
I don't know. I believe that's right. They don't. Everything was pointed out, I think, in a paper of Devore and Ranyuk and somebody to do everything directly from it. But of course, for some applications, you want to have explicit or matrices. So there's a lot of work done on making them explicit.
I see.
And also on to make them computationally well, the number of steps to build them should be small too. The complexity of them, and this has also been stuff done. Forgotten the names of the people that worked that out. So yeah, there's a lot of stuff done on that. But if for theoretical purposes, all you need is any construction, do random constructions, and that's maybe the simplest. And in principle, gives you the best estimate. Actually, Asaf said that, pointed out that even without knowing what the best estimates are in JL, he worked out that doing a random projection actually gives you the best estimate. I haven't seen the proof. He told me he actually proved that. I don't know how that's proved. So if you care by best estimate, I mean for a given epsilon, you want to have the maximal little n. And just absolutely the best estimate is gotten by a random projection. So that's a little bit of a surprise.
Wait, they proved you can only get it by a random projection, or
no? Just abstractly, if you know if you have a method for getting the best estimate, actually that's achieved by the random projection. This is what he told me. But I don't think he ever wrote this up.
Yeah.
See, it was Jelani and Nelson and his collaborator, who computed that the estimates in of the dimension n of little n from capital N for a given epsilon is the best possible. You know, it was computed, of course, a long time ago what works, but to compute that was the best possible for any even nonlinear mapping. That's very recent. That's only about, what, 2 years old.
Oh, I see.
But that was more difficult because they were looking at true nonlinear mappings. In RIP, it's very important that the mapping be linear, right?
Yeah.
The original application that Yorm and I had for it, we didn't care that it was linear. Of course, we're only interested in the operator on a discrete subset, on a finite subset. And the fact that it has a linear extension, you know, okay, that's nice, but so what? But when you go into compressed sensing, it's essential. And for many other applications too, it turns out to be essential that is a linear mapping.
I just looked it up. Candice Tao, according to Math Science Net, is only his 4th highest cited paper, Tao's, and it has a slim 700 citations, according to Math Science Net. So
700?
Only 716.
That's Math Science, but look at Google's.
Google's going to be a different world because it's one of these IEEE papers, so it's going to be cited thousands of times.
Yeah, well, you have to look at Google Scholar because it'll be cited outside of mathematics very often.
And I guess that counts.
Well, it depends on what you're counting.
Yeah.
Well, Google doesn't exclude fake journals, so.
Oh, that is true. Yeah.
Well, even so, it gives you the best count for general science. If you have things that are being cited in many different areas, MathSciNet only gives you a collection of.
But Google will be inflated.
Well, it went up to 7,800. So
on the website Merriam-Webster.com, they say,
hey, Google, go to sleep.